All right, we're going to do problem number 35. 35 reads, what value of a and b make our function f of x equals x cubed plus ax squared plus bx? What makes it have a local max at x equals -1 and a local min at x equals 3? That's part A. And then part B is independent, so once we get A, we don't need that anymore to get part B. Part B is a local min at x equals 4 and a point of inflection at x equals 1. So we're going to begin with part A. In part A, we want a max and a min. So immediately you're thinking, I need to take the first derivative. I'm looking for critical points. So we take the first derivative, and we notice it's a polynomial, so it will be defined everywhere. So our critical points will be when the derivative is 0. We're not worried about the undefined part. Our derivative gives us 3x squared plus 2ax, because a is a constant, and then plus b. Now, a couple things we'd like to do. We'd like our derivative equal to 0. We want critical points when x equals -1 and when x equals 3. So we'd like critical points at those two values, when x is -1 and when x is 3. So now that I have the derivative, I'm going to sub in those values, and I know that derivative should equal 0 at those values. So I'll take f prime of -1. I sub that in. Looks like 3 minus 2a plus b. And if that truly is a max, then this derivative, I should have a critical point there, so the derivative at -1 should be 0. When I put in the 3, the same thing should happen. So this looks like a 27 plus a 6a plus b. And if we look at this, we have two equations. We have two unknowns. We have two equations, two unknowns. We can solve this. So we're looking now at these two equations right here. And again, how do we get those equations? Well, we knew there's a max and a min at -1 and 3. For a max and mins to occur, they need to be critical points. And a critical point is where your derivative is 0 or undefined. And it's a polynomial, so we knew the critical points had to be 0. The easiest way to solve these two equations would be to subtract the two, because that will cancel out the b. So I'm going to subtract the second equation. I get 3 minus 27. I get a -24. A -2 minus 6 is a -8a. Look at that. The b's go away. And 0 minus 0 is 0. I can solve this now for a. I'll add 24 to the other side. Divide. And it looks like a equals -3. Now that I know a, it's not difficult to go back and get b. I think I'll get b from the first equation. So I'll write 3 minus 2. I just figured out a was -3 plus b equals 0. So I've got 3 plus 6 is 9 plus b equals 0. So it looks like b equals -9. Now we haven't had any choice in the matter. So these points need to work. A has to be -3 and b has to be -9. It's not like we have any other options. But we still need to check and see if this truly gives us a max at -1 and a min at 3. And if it doesn't, we're kind of out of luck. It's just a bad problem. But let's just try it anyway. Let's go back. We've got a is -3, b is -9. Here's our function. We're going to go with x cubed. So our function now would be x cubed. A is -3. If we sub that into the function, we get -3x squared. And b is -9. So we get -9x. And now our hope is, when we find our critical points, we'll have a critical point at -1 and 3, and it truly will have a max at -1, and we'll have a min at 3. So let's go through this just to check it and see. Let's take the derivative. And the derivative, I get 3x squared minus 6x minus 9. I want my critical points. I set that equal to 0. I'll factor out first a 3. I get x squared minus 2x minus 3. And I factor that, and no big surprise here, I hope. When I factor that, I get x minus 3, x plus 1. And look at this. Two critical points. X equals 3, x equals -1. Now, Let's see, are these max or mins? And probably our easiest way to check is the second derivative test. So from the first derivative, I'll take the second derivative, and it looks like a 6x minus 6. I'll sub in my -1 first. I have 6 times -1 minus 6. It is negative. My second derivative is negative, therefore I have a max when x equals -1. Let's sub in back to our second derivative, put in a 3, and it looks like 6 times 3 minus 6. I have a positive value. And because my second derivative is positive, I have a local min at 3. Let's go back and double check one more time what we were given to do. And look at that, we found it. We created a local max at -1 and a local min at x equals 3. Now we're ready for part B, and part B is the same, certainly the same idea as part A, slightly easier because we have a point of inflection in here. So let's transfer our function over to a blank page, x cubed plus ax squared plus bx. So here's our function. It's the same function, x cubed plus ax squared plus bx. And now they asked us for two things. And again, there's two unknowns, so it kind of makes sense. There's two things they'd like. They want an inflection point. I forget if they wanted a max or min. Let's go back and see what they wanted for part B. So part B, they want an inflection point when x is 1, and they want a min at x equals 4. So an inflection when x equals 1, and a min when x equals 4. So that's kind of our charge to find those. And we will do it in the same way. So let's take first our first derivative. And we get the same thing, 3x squared, 2ax plus b. They have inflections, so we might as well find our second derivative, which gives us 6x plus 2a, and the b goes away. So we'll begin with our inflection because that only has one variable in it. And if there's an inflection point at x equals 1, I know if I put 1 into the second derivative, I should get a 0. So I'll put 1 in for x, 2a, and my second derivative should be 0 when x equals 1. So as I solve this, I get 6 plus 2a equals 0. Solving that, I'm going to get a equals -3. That should be the inflection point. We will check this at the end and make sure that truly is. But again, we had no other options on here, so this better work out. Second part, we've got a min. And so we'll look at our critical point here. We've got a min when x equals 4. So I go back to the first derivative, and I'm going to sub in 4. So I get 3 times 4 squared plus 2. I just found out a was -3. X is 4 plus b. And this whole first derivative at x equals 4, this whole first derivative needs to equal 0. Why? Because it has a min at x equals 4, and mins occur at critical points. Local mins occur at critical points, and a critical point is where a derivative is 0 or undefined. So let's solve this. Shouldn't take too much work. 4 squared is 16, so it looks like a 48 minus 24 plus b equals 0. So solving that, it looks like b equals -24. So now let's just double check our function and see what we've got. We've got our x cubed, and it was -3. A was -3, so -3x squared minus 24x. So this is our check now. This is our answer. That's our function. Oops. That's our function. Let's check it to see if it truly works out the way we thought it did. We'll take the derivative, 3x squared minus 6x minus 24. Let's take our second derivative, 6x minus 6. When I set my second derivative equal to 0, I can see I have a possible inflection point when x equals 1. I could make a quick little chart here with my second derivative. And if I put in a value less than 1, like 0, true enough, the second derivative is negative. A value bigger than 1, like 2. 6 times 2, so put it in again for the second derivative. 6 times 2 is 12 minus 6. It is positive. And so x equals 1 truly is my inflection point. And again, I'm just checking the answer. So far, so good. Now, let's try the second derivative. I'm sorry, the first derivative. And I want to make sure when I put in 4, was that our point? Yes, I want to have a min right here. A min when I put in a 4. So let's try that and see. My first derivative was this 3x squared minus 6x minus 24. I could factor this and find out my zeros, or I could just sub in the 4 and see if it truly does give me a 0. This is 3 times 4 squared minus 6 times 4 minus 24. And look at that. 48 minus 24 minus 24. That really is 0. Now, is it a max or is it a min? Let's use the second derivative test. And look, guys, we've kind of done that already. Because when x equals 4, that's between 1 and infinity. And we know our second derivative is positive. So when we put in a 4, our second derivative is positive. Therefore, x equals 4 truly is a local min. And so we've checked our answer. We came up with a equals negative 3. We came up with b equals negative 24 for our two answers. And that completes our problem.